Right. Hello, Lorena from Spain. Okay, with no further delays, let us start with our analysis seminar. The analysis is going to focus on crosshole ultrasonic testing only. And as you know, this method is a bit easier to analyze than the sonic tests and other methods. However, there are some, or quite a few pitfalls where you can fall. So we're going to go into the very basics to understand what are the parameters that this test is doing and see how to combine them together to get some proper analysis. First of all, a little bit of motivation. So why do we need to test at all? As you can see, this pile was uh, cast with polymer slurry. Some problems were found. If you will look carefully here, where I mark, you can see the crosshole tubes of this pile, and of course, the path between them is void. So this was uh, quite an easy defect to test, to find. Another example is here. Here it's a bit harder to see, but the tubes are here. And of course, it was quite easy to see this defect. This was a diaphragm wall cast with bentonite, very defective. So that's about the motivation. And let's really talk really quickly about what we're going to talk today. So I'm going to give a very short intro to crosshole ultrasonic testing, which is dubbed CSL, crosshole sonic logging. And then we're going to talk about which parameters the system is actually measuring, which are time and energy, how they are combined into an acceptance criteria, or criterion, actually a single. And then um, once we have a criterion, our job is not done, because every criterion has some false positives or false alerts. So the criterion will tell us, hey, there's a problem here where there is actually none. Um, so we have to actually understand them and understand where we need to apply engineering judgment. At the end of the presentation, I'm going to give you a bonus preview on a new interpretation and analysis tool that is going to join CHUM soon. It's quite rudimentary, but it will still give you a very good taste of what is coming up. Okay, as I said before, there is a chat window below that you can just click and ask your questions, and the questions are going to be moderated by Gadi. I will try to answer them in real time, otherwise at the end of the presentation or offline using email. Whenever I'm speaking too fast or you want to go into details or something isn't clear, you wanted to repeat it, raise your hand using the raise hand button. The icon is below, and as you can see, I raised my hand. So it's very easy to see. You can try that now. Press it again to lower your hand. Okay, let's go. Crosshole ultrasonic testing is done this way. You have a pile with two access tubes, at least two access tubes filled with water. Into these tubes, which are water filled, we lower the receiver and transmitter, and we lower them to the bottom of the pile and start pulling together. As we pull, the emitter is transmitting data to the receiver, and the system is recording the arriving signal. It's recording both the arrival time and the energy. When we finish pulling all the way to the top, we can test another tube combination if we have any, or we can go to the next pile to analyze it. The data that we pull is going into some signal conditioning box and then into a computer. The access tubes arrangement can be just 2 tubes, 3, 4 tubes, or more. And the more tubes you have, the more combinations. So when you have 4 tubes, it's already 6 combinations, and the number increase polynomially. The more tubes you have, of course, you have better coverage, but remember that the tubes also cost. So it's the rule of thumb is that for every 1 feet of diameter, you need 1 tube. So if you have a 1 meter pile, which is approximately 3 feet, you would use at least 3 tubes. And for a 2 meter pile, you can go up to 6 or 7 access tubes. Let's see a 3 minutes video. That's all, just 3 minutes, I promise, about how the testing is performed. Okay.
On this site, large diameter board piles were constructed. On the surface, they all look perfect. But are they? CHUM, compatible with ASTM standard D6760, looks for the subsurface imperfections through the access tubes installed. Depth meter pulleys are placed on top of the water-filled tubes. Ultrasonic dual-function transceivers are lowered into the tubes. And lowered together all the way to the bottom, which may be 100 meters below ground level. When the sensors are level, the computer connected to the CHUM gives the order pull. While both cables are pulled together at a speed as fast as 2 meters per second, the location of the sensors is shown on the screen in real time. Ultrasonic pulses are continuously sent from the emitter to the receiver, and anomalies, such as increased arrival time or lower energy, are immediately displayed. CHUM automatically adjusts signal gain for optimal signal quality under variable conditions. CHUM also supports 2D and 3D tomography. Both sensors exit the access tube together, and the ultrasonic profile is already on the screen. First arrival time, relative energy, wave speed, and the waterfall presentation. Other profiles are logged the same way. The data is analyzed by the engineer who checks for any inconsistencies, adds his comments, and prints the report.
Okay, let's conclude that now. And I really apologize for those of you who have already who are very familiar with that already.
On this site, large diameter board piles were constructed. On the surface, they all look perfect.
I will
But
go
are
to the
they?
next slide soon.
CHUM.
Yeah, okay. So what parameters are we actually testing? The system is actually measuring arrival time and energy. Let's talk about the arrival time. Arrival time is, or sometimes it is called time of flight, but we prefer to use a first arrival time, dubbed FAT. The arrival time is influenced by the wave speed and by the path length. So the faster the material or the faster the wave speed of the material, then the wave will arrive sooner. And the longer the distance, the longer it will take the signal to arrive. Just like when driving a car, if you have longer distance to drive, it's going to take you longer. If the road is not as good, it's going to take you longer. Fat is not a very well defined physical entity. I mean, there is no one formula that I can put the signal into and to get the arrival time. So fat is subjective, and we're going to discuss that in a very short time. Why is fat subjective? And there's a one big word that influences all physical measurement: noise. Yeah. So this is a very easy case. I mean, you can see the signal here, very clean signal here, and then the arrival time is very easy to see. The signal just comes here. That's a very clear case. But in this case, there is a lot of noise here in this area. So it makes it very, very problematic for any algorithm or any system to analyze the data. In these cases, the human eye is the best algorithm. However, when we are testing a pile, it can be thousands of signals, and going through them manually is very tedious. The reasons for the noise can be electronic, they can be acoustic, and more. Now, I have placed read more links in the presentation. The presentation is going to be shared with you. So any one of you who wants to really learn more about this subject or another subject is welcome to explore things which are just out of scope for this presentation. The arrival time, or FAT, is just a very easy way to calculate the wave speed. We just have to divide, the wave speed is just a function of the distance and the time, like with a car. Distance over time means wave speed. Once we have the wave speed, we can sometimes correlate it with the concrete compressive strength. And why am I saying sometime? Because this CHUM is actually just measuring time. What we can see at the top of the pile is just the distance between the tubes at the surface. The tubes can be at a different distance below, and then all the wave speed calculations are wrong. And as a result, also the compressive strength calculations are wrong. As you can see here, the compressive strength is a function of the wave speed to the power of 4. So that means that it's a very sensitive function. When we have just a 10% drop in wave speed, which is very easy to miss, it's going to create a 33% reduction in the tube strength. And that's a lot. That means that the wave speed should be measured very, very accurately, and that the results that are showing concrete compressive strength should always be considered with a good engineering judgment. And we will see examples for that in the future, in the next. So as I said, FAT is actually an algorithm. And as I said, also the best algorithm is the human eye. Now, we have to find some way to combine the two, because it's not easy for computers, but it's also too tedious for humans. So let me actually demonstrate that for you inside the CHUM software. I'm going to jump quickly into the software. Let's open just any pile here. And okay. Can you see that? I think you don't. I'll have to change the sharing to the entire screen. Can you see that now, Gary? Yes. Okay, so what you see now is the FAT utility. We can see a lot of signals. I can change here the column width to show them a little clearer. So some cases are really easy, like here. I can scroll and can see that. But as we enter a defect, the signals are getting weaker and fainter. And for example, in this case, it's very hard to really determine if the first arrival time is here, or maybe it's here, or maybe that's just noise and it's here. We have to look at the other signals above and below and apply some judgment here. And that's why I said it's a subjective thing. Now, even though it's subjective, CHUM really helps us in that process. And we can press here the calc button. When I press the calculate button, I can then just, in this case, I only have one calculation option. I press OK, and it recalculates everything. So let's say, suppose I had here, suppose I had some places with wrong arrival time peaking. I'm jumping forward. Something that looks like that. Something that looks like that. We can go into the FAT utility, and then we can either fix them manually, or we can do a calculation which will fix them for us. Calculation is not always perfect, and that's why we can do a manual override. Now, manual override is not cheating. It is just understanding that any computerized algorithm can sometimes be a little bit wrong in these cases. By the way, these signals look very familiar, very similar to signals that we get from earthquakes. Just a different frequency and magnitude, of course, but the nature of the signal is the same. And you know what? Also in earthquake studies, where the time is very critical in order to calculate the epicenter, a human eye is always involved in the process in order to make sure that really they get the right location and the right time for the earthquake. So let me go back in here and again share my presentation. Okay, so that was about fat picking and why we need to do it manually sometimes. The next, oh, hang on. I also want to show you another screen. So let's do it like that. I will share that screen. Yeah. Okay, so now you can see the FAT screen, the CHUM, sorry, software screen. I'm going to enter a self-test mode here. And you will be able to see here a live signal. If you look at my video, you can see that I'm holding two sensors. And as I change the distance between the sensors, which are now disappearing because I have a fake background, let me delete that fake background. How do I do that? Yeah, okay, I'll just hold them at face level or like that. And you can see that as I increase the distance, the arrival time changes. So I'm doing it a few more times so you can look both at my video and on the screen. I hope that's clear here. What I want you to see is this window here, and you can see that this signal moving back and forth as I change the distance. Fine. So that was a simple example of how distance changes the arrival time. And let me return to our presentation. Good. Okay, the next parameter that we want to test is, or not that we want to test, the next parameter that the system gives us is energy. Now, in a homogeneous material, such as solid concrete, yeah, I've got a hand from Sweet Pepper. Can you please write in the chat window what you need me to do? Is there a question? You can unmute your mic and ask. Okay, I'll wait for your question in the chat window and continue for now. Oh, is there a recommended minimum or maximum distance for the test? Okay, excellent question. So what governs the minimum distance is actually cost. We don't want to go into very, very small distances between the tubes. That would require too many tubes. Also, in a very small pile, sometimes it's really cramped to add the access tube. So if we have a 30 centimeter pile, the cage is going to be like 20 centimeter, and inside that, the tubes are going to be just too close. So that's not a good case for testing. So that's the minimum distance. And I would say that 30 centimeters between the tubes is really an absolute minimum to get a reliable test. And for the maximum distance, what governs that is the size of the defects that you want to see. Now, as a rule of thumb, you can only see defects which are about third in size of the distance between the tubes. So if you have a 1 meter spacing between the tubes, you can see a defect which is about 30 centimeters, about the size of a basketball. If you have 2 meters, it's going to be already 60 centimeters, which is a very, very large defect. So that's why the rule of thumb is usually one access tube for 1 feet of diameter. If that means that you have about 80 to 90 centimeters between the tubes, which is a very good distance for testing. You can really see good size defects and not waste too much money on access tubes. Hope that answers the question. So we now continue with the next parameter that the system gives us, and that's energy. Energy is just how much strength the signal still has when it arrives to the receiver. And the energy is a function of the energy that we transmit. And that is multiplied by e to the power of a constant k, f, which is the frequency of the ultrasonic wave, and x, which is the distance. Now, we actually have no control over these constants and frequency. They are fixed. So it's actually just a function of how much energy we transmit, which we also have no control of, that is fixed in the system. So it's just a function of distance. The more distance we have, the lower the receiver energy is going to be. And that's the only factor that actually controls the arrived energy. However, material properties are also a big factor here, and that comes in K. When we have a weaker concrete, it has a different constant here, and we're going to get a lower energy. Now, the nice thing about energy is that it is objective. We can just put energy or the signal into a very simple and well agreed upon mathematical formula, and we get the energy. There are no arguments there. There's nothing to change or to pick. It's a fixed and well-defined entity, the energy. And I'm going to show you that, again, using the same probes that I tested before. I'm going to show you that. And when I will increase the distance between the probes, you will see that the energy is also changing. So I hope you can see my screen now. Gary, please confirm. Yes, okay. So I'm going to go again to the same screen. And again, I'm going to show you the arrival time. But we don't care now about the arrival time. What I want you to see is this here, where my cursor here. You can see the strength of the signal. And as I go farther and farther, the signal is getting into a smaller scale, smaller and smaller scale. So you can see that the strength of the signal, not just the arrival time, influenced by the distance. Now, another thing that influences that is the material. Right now, the signal goes through air. If I will change that and will make the signal go through my body, which is mainly water, you can see that the signal becomes, much, much stronger. Again, I'm not, right now it's touching my hand. When I disconnect, it's immediately 10 millivolts. Touching my hand, 1 volt. Not touching my hand, 100 times weaker. So that just shows you that my hand, or water for this purpose, is a much better conductor of ultrasonic waves than air, which is a very poor conductor. Again, not touching, touching, a much stronger signal. Not touching, touching. Okay, I think that really explains this matter, and we can go back into the presentation. Yeah. Okay, so we are here, and how I don't get a very clear presentation window now. Hang on a second. Okay. Next thing about energy is that it's very easy to convert it. Can you see it? What? Sorry? We don't see what you see. Okay, let's try that again. Okay, sharing. Okay, can you see that now? Okay, so we can convert energy to decibels, which is a very simple formula, just 20 log, and the energy at the receiver divided by some reference energy. We use a very high reference energy value so that this fraction here is always greater than 1, so we don't get negative decibels. The nice thing about decibels is that it is linear. And another nice thing about decibels is that if we take 20 log half, 0.5, we will get approximately 6. So it's very easy to remember that 6 decibels is about 50% reductions. If we have 12 decibels, that's 6 plus 6, that's 50% of 50%. That's a 75% reduction, and so on. You can also, when you get the presentation offline, you can read more about it. It's a very convenient way to work. So right now we have time and energy. Both are linear with distance, which makes interpretation a bit easier. When we need a way to see how to combine them into a criteria. Let me go back into CHUM. Yeah, share. And I'll just open any file. Okay. And can you see that? Yeah, you can see that. Okay, so here we have the basic presentation of CHUM, and here we can see in the red line the first arrival time, and the blue line is the energy. So we can see that in this area here of the pile, the arrival time increased and the energy dropped. That's clearly a problematic area, where is in all the other parts of the pile, everything is uniform, both the energy, although it's a little bit more wavy by nature, and the arrival time. So that's a clear indication in CHUM of a problem. And we're going to go into analysis of that really soon. So I'm going to present the presentation once more. Okay. Now, acceptance criteria, or criterion in single. For many years, every agency, every testing laboratory, every specifier had their own criterion, which was specified. In 2020, we set together a task force of experts, and we formed and proposed a rating criteria, which we called DFI, Deep Foundation Institute 2020. The proposal is now widely accepted, and you can link it. You can see the view and the full document offline. And note that some places, for example, California, China, and many other places around the world, are not using these criteria. They have their own criteria, homegrown criteria, and they don't want to replace it. So you need to adapt to that. Let's talk about the DFI 2020 criteria, which is criteria goes like that. There are three classes of problems. A class A is everything good. Class B is conditionally accepted or questionable anomaly. And class C is highly abnormal. There are also color coded to the same colors as a traffic light. And they go like that, from 0 to 15% good, 15 to 30 questionable, above that is bad. Okay, we combine into that also the energy to get a chart like that. So here is the arrival time, here is the energy or attenuation, and you can see that as long as we have less than 50% arrival time, less than 9 decibels change, all good. Beyond that, the things get a little bit more complicated, but it's still not so hard to understand. So between 15 to 30% fat, it's questionable. However, if the the energy is also increased, then it's considered highly abnormal. And above 30% fat, we don't care about the energy. It's highly abnormal. So fat is the main criteria. Energy is a supporting criteria. How do we see the acceptance criteria in CHUM? I'm going to jump again and present again the CHUM window. And when we go into any profile, you can see here in the presentation the option to add or to remove the classification bar, which is this bar here on the left. So when I add the classification bar, I can see that traffic light, green, yellow, red lights. In addition, I don't know if you can see that, that's on the right of the screen, and I cannot move the mouse there because once I move it, it disappears. You can see each pulse is a little red dot that bounces around and show you how it's classified. So all this area here is green, and then outside of that, it goes to the red. I can also drag and drop a selection of area, and you can see all these points where they are located. So here, this area is good, and problems here. If we go into the actual classification bar user interface, you can see how it is. And we can select either a global criteria or local. We're going to go into that in a minute. Or you can even use your own custom criteria, which I hope you will never use. It is just staying there for backwards compatibility. So that's the DFI criteria. And okay, so I demonstrated that. Let's go into false positives. Why do we want to talk about false positive at all? The reason for that is that it's very easy to think that once we have a criteria, our job is done. We have a computer choosing for us red, green, yellow signs, and that's it. And we just have to show and present it. But that's really not the case. We need a case to understand. We need to apply engineering judgment into that and to decide where abnormal result is actually a flow. Abnormal result is anything that we did not expect. We expect a straight line, we have some deviation. A flow is actually a change in the pile, which is not according to the specification. And a defect is that a flow that is also severe enough to reject the pile. Now, a false positive is that we have an abnormal test result in area 1 here, which is not a flow. Why do we get that? So one reason is operator error. For example, not pulling the cables together, then we get different distance between the tubes, larger distance, larger time. Another thing is operator error or software error where we did not pick the FAT correctly. Next thing is installation error. For that means, for example, the tubes are not parallel. The tubes were welded with excessive sleeves that created some kind of a gap. Debonding, typically in PVC tubes, that's a problem. Or even sometimes we forgot to put water in the tubes. And of course, there's also a reason for hardware error. If you have an old system which is already loose contacts and worn out, that's a problem. Let me show you a demo, or actually 2 demos of that, if I have the time. So I'm going to share my entire screen 1, share. Can you see that? Yeah, and I'm going to CHUM again, and I'm opening this file. Can you see this result here? Can you? Okay. What you can see here is that we have a very straight first arrival time, the red line. However, it's straight, but it's not uniform. It's increasing gradually to the level where here the software pick it up as questionable, and at the bottom has to pick it up or to classify it as a defect. And now, maybe it's hard to see, but you have here a very small red dot, and that's the reference FAT against which the software is comparing all the other FAT values. Can you see that somehow? Yeah, okay, you can see the red dot. So that's clearly an installation error. The problem here is definitely not a problem with the pile. The problem is with the installation, and the location of the tube does not change the quality of the pile and is not an indication of a defect. So if you apply engineering judgment, you look at the cages on site, and you can see that the contractor is not doing a very good job in attaching the tubes to the cage, then you can definitely write that in a report, and you can save a lot of money to the contractor and a lot of trouble and time by just applying judgment and saying, guys, this is not a flaw, this is not a defect, it's just a false positive. The criteria is missing here because the criteria cannot think about non-parallel tubes. Another example that I have here is here. That's quite a big pile. So I'm going to scroll down all the way to 50 something meters. And you can see here a very clear sign of a problem. However, this was totally expected. Why is that? That's a buried check. That was a static load test file. That's a buried check. So you cannot really call that a defect. You have to call it out and say, yeah, we found the check. That's expected. It's not a flaw in the pile. Even though you can see here the red marks and all the bells are ringing. Okay, so back to the presentation. So just to summarize that, a criteria is not good at all unless you apply some engineering judgment. Now, Gadi, tell me if you have time for that. Yeah, okay. So tomography is really a huge subject. And I think it justifies a whole new webinar sometime. However, I just want to give you a 1 minute, 2 minutes preview of what tomography, 2D and 3D tomography looks like. And I just want to tell you that not all defects can be imaged. If you have a defect that is very close to the bottom, like a soft bottom, very close to the top, you just cannot reach it with diagonal readings. You cannot really do a tomography there. I'm going to show you a demo of that. Again, presenting entire screen. Share. Okay. So I have here a little bit of a wizard. Sorry about the background. Maybe I can move it around. Okay, not here. Here. Okay. So I'm going to select a pile. I'm going to ask it to calculate the tomography for me. And I have this view. Now let's go over this view very quickly. On the left side here, I have a palette that's showing me the wave speed. Red means very low speeds. Blue is similar to speeds of water. Greenish is mixed concrete, and gray is concrete as we expect. Here on the next pane, we have horizontal slices. Next one is vertical slices, and the top is where I want to slice from to, the AB, the two locations of the slice. And this pane here, I can see a 3D image of the pile. I'm going to make it a little smaller. All these panes work together. Now, you need to understand that what I actually see is areas of lower velocity. That's what I'm looking for. So I got a threshold value here showing me which velocities are transparent. So let's put that in 2,500. And now I can see defects where, or areas in the pile where the wave speed is below 2,500. If I will look down, I can see that I have a problem here at around 8 meters. I can look at it from all directions, rotate, and I can even slice it, move it through some kind of a slicer here. When I move it through the slicer, I can see it here on the horizontal slice. And I can even get here, I don't know if you can see that, but some kind of an effective area of the slice. So that's a very impressive view, but it requires quite a lot of work that has to be done very, very carefully in order to be viewed to this level. Again, going up to the top of the pile, and I can go and scroll all the way down to the bottom and view the pile from any angle. So it's very impressive. You can even present your result in a video if you want. You can take screenshots and attach them to your report. And I'm not going to discuss this much right now because as I said, it's a huge subject, but I am going to show you a bonus preview, as I promised, of something different. And that is a feature that is about to enter CHUM. This feature is called horizontal slices. Horizontal slices is taking all your usual normal testing results, either tomography or non-tomography, and processing them together to get horizontal slices at any given depth. So here, again, it's a very rudimentary presentation now. It's going to enter CHUM in a very much nicer way. But here, for example, here is a good area of the pile, and we can see that we have all gray, no problems. But as we go here to around 7 meters, if I remember correctly, we have some problems here showing. So we can see a horizontal slide, and we can see that here, we can see that we have just 27% of the compression strength left in this pile, while in other places where I stopped, here I got 95%, etc. If I go up to the top of the pile, usually it's already where the axis tubes are starting to be outside of the water. So we have a very little residual strength length left. Now, if we will plot this mean wave speed against depth, we will have a new way to present data in our report. And excuse me, going back to the presentation. Yeah. Okay, so we're going to have a new way to show the pile as a whole, not just individual profiles, but the whole pile as a whole. It's a very easy way to view and understand the status of the whole pile as one piece. And that's going to go into CHUM as a preview quite soon. I hope in a couple of months it's going to be ready for you, for public consumption as a initial beta. That actually concludes our presentation. You're most welcome to add questions to the chat window. Yeah, Lara Miguez asked if it's going to be possible to get a recording. Yes, we're going to send a recording of the presentation, and we're also going to send you the slides. So you can see click on the read more links and learn about it. So I'm going to give you a couple of minutes for questions, and if none, then I really want to wish you all a very good day, and thank you for attending our crosshole ultrasonic presentation or analysis presentation. Thank you.
Sorry.
Sure, Anzor.
Can you hear me?
Yes, very well.
First, thank you for the good presentation.
Thank you.
I have just one question for the tomography. I'm using 12 version, but when I clicking the tomography, there is nothing. We need to buy some access for this, or normally can we use how it's work? Can you explain, please?
Okay, standard tomography, two-dimensional tomography is part of the software. If you have two identical depth encoders, you don't need to buy anything else. You need to use the Y cable. Remember the cable with two ends, the red and the green? You need to go into the user manual and learn about tomography because there is a lot to learn. It's not a trivial test. You have to do it very carefully. So study first, practice in the office, and only then do it in the field. But you have everything that you need, or you should have everything that you need to do the tomography on site. And then you can do a two-dimensional tomography.
Yeah, normally we don't need for the reporting because in Georgia, I'm from the Georgia, here is a so small project, and the clients also actually doesn't paying so much for the tomography, and just we need to show clients because sometimes Pile has a so small problem, and just I want to show from the tomography there is no any big problem, and I tried on the site, but the problem was I think I don't have access, or if I can share.
Yeah, you're talking about three-dimensional tomography, probably. Three-dimensional tomography is a product that has to be purchased separately, and we can do it for you for a few piles and a limited time period, just to get you started. Another thing about tomography is, yeah, you need the processing engine to do it, but you should have everything ready, and you can do the two-dimensional tomography on site. You have everything already. One more thing, I once had a case where a small defect was found in a 70-meter long pile, and the defect was at around 65-meter deep, and it was quite small. And tomography showed that the contractor was really willing to pay a fortune for the tomography, because using the tomography, the specifying engineer decided to accept the pile with a small penalty for the contractor. It was a friction pile, so he did not really care much about what's going on 65-meter deep. And it saved the pile for the contractor. You can just imagine how much money a 70-meter long pile, 2-meter in diameter, costs. So sometimes the contractor is really interested in tomography in order to really save pile in specific cases. I mean, sometimes it will not help him, but in cases that it will, it's a lifesaver. More questions? Okay. Oh, Kevin.
I would like to know what kind of results or what kind of conclusions we can take after this test.
Okay. Well, as I said during the presentation, the system is measuring time and energy. Okay. You cannot say that a defect that you found is due to honeycombing or segregation, or is it a crack, or maybe a small soil collapse, soil inclusion, slurry mixed with the concrete. You just cannot tell that. All you can say is that the energy has dropped and the time has increased in this level. So a typical conclusion that you will say in your report is a severe anomaly at 10 meters between tubes 1 and 2, something like that. Or you can even say a big flow at this level. But you cannot really say what's the reason for that. That's really not, you don't have a camera, you don't take concrete samples. You just know that the time increased the energy dropped. That's all.
Thank you.
Sure. Any more questions? We are reaching the end of our presentation, so I really wish you all a great day and thank you all for joining us. Thank you. And you're welcome to send us questions offline. Thank you, Jamil.
Can I ask one more, please? It's answer.
Who is it? Kevin. Yes, sure, Kevin. Thank you, Matthew.
We have one project in Georgia now. We making measurement for the Barretta. Normally, we need the designer needs to make 8 tubes, but our CHUM program there is 12 or 6. Should I make like this? Should I measure? Should I choose the 12 tube and after can I delete? It's change something?
I'm sorry, but in CHUM software you have more options. Let me show you that.
Yeah.
Entire screen. Somehow I cannot share anymore. Daddy, is there a reason? Stop. Entire screen. Screen 1. Sharing. And whew. Okay, so I'm just opening a project, adding a pile, and here,
Yeah.
can you see that? I can select 8 tubes.
No, it
Normal.
will be Barretta. It will be
It's
Barretta.
already built in, yeah, it's built in, and then press all combinations. It's going to do these things for you, or you can do just the peripheral. Usually in 8 tubes, you don't need to do all, so you can do just a few like that.
Yeah.
And test them, and if you find a problem, then you can do these too. Okay.
Yeah,
So,
but
and
our pile is a rectangle, you know. And
a rectangle. Okay,
yeah.
so let's clear that and select
it will be Barretta.
a Barrett. Yeah. So you
And will
can
be
use the
totally
you can use wall 10 and just use the first 8 tubes. Okay, so
Yeah.
I'm gonna. Okay, you don't need these two.
Yeah, then I will delete from
Yeah, you just delete it and then you report what you see. You're not gonna see these in the report. You're not gonna see 9 and
Yeah.
A. Okay,
Yeah,
that's the
sure.
way to go.
Okay.
Sure.
Yeah.
Okay, that's really a bit off
Thank-
topic of our presentation. So I would rather have only questions about analysis, and other questions you're most welcome to send me to support@Piletest, and I'll really be happy to answer you.
Thank you. Thank you so much.
Thank you very much. Thank all for
Thank you.
sharing, for joining, for asking questions. I hope it was interesting. Bye-bye. Have a great day.
Thank you. Thank you again.
Thank you. Thank you, Stanislav. Thank you. Thank you, Ansur. Bye-bye.